Hello all. In our previous lecture, we defined the traveling salesman problem and we formulated this problem. We developed the mathematical programming formulation. Remember that TSP has a close relation. The formulation of TSP has a close relation with the assignment problem. But in addition to the assignment problem, we need the subtour elimination constraints, which is the complicating constraints for this problem. In this lecture, we will consider an example. We will write those closed form formulations as an open form so that you can understand it better. And then we will learn the steps of the branch and bound algorithm for the traveling salesman problem. Because we have a different idea, another idea of branch and bound for the TSP. And in the following videos, we will also talk about heuristic algorithms to solve the TSP. So let's get started. So the traveling salesman problem is difficult to solve. But when we say difficult to solve, don't be confused. The problem is easy. It's easily defined. And when we say difficult, it doesn't mean that you need to make a lot of complex mathematical operations and etc. When we say difficult to solve, we are talking about finding the best solution, finding the optimal solution. And the difficulty comes from this fact. It takes time to find the best solution. Especially when the size of the problem is larger, it requires a lot of time to solve it, and we call this as the computational time, the time to evaluate the alternative solutions and find the best solution. For this purpose, we may utilize different solution methods. So we already learned about the branch and bound algorithm. So we can use the branch and bound algorithm to solve it because it's an optimization problem, and in the previous lecture we formulated this problem. Okay, so by using this branch and bound algorithm we can solve it. We can utilize the cutting plane algorithm, but still branch and bound algorithm and the cutting plane algorithms are efficient. It means that they evaluate the solution space in an intelligent way, but still there are many optimization problems which takes a lot of time to solve with these branch and bound and cutting plane algorithms. Although they reduce the solution space too much, still the remaining part is a lot and it takes a lot of time. Therefore, we need some other methods. So we need heuristic algorithms to solve these problems. Heuristic methods are computer algorithms. They are they define you the steps of the solution procedure, and heuristic algorithms do not guarantee optimality, but they provide you a good solution, a feasible solution in less computational effort. Therefore, heuristic algorithms are very useful, especially for solving large problems. Okay, so in this lecture, we are going to talk about a branch and bound algorithm to solve TSP, and we will talk about a different version of the classical branch and bound algorithm. And we will talk about a number of heuristic methods to solve the traveling salesman problem. So let's consider an example, and let's first formulate this example problem, and let's try to develop a branch and bound algorithm for this problem. Okay, so this example gives you a different application of the TSP. Let's see how the problem is defined. Okay, there is a company which produces different colors of batches, which produces items with different colors, and each batch can be either white or yellow or red or black. And depending on these colors, okay, so you need to clean up the machines before you change from one batch to another. Because if you do not clean up, for example, you assume you produced red items, and then from red to white, if you change the batch from red to white, if you do not clean up, because of the remaining paint on the machine, which is red, the white does not appear to be pure white, but it becomes something like pink. It includes pigments of red color. Because of that, you need to clean up the batches, you need to clean up the machines between the change of these batches, and a proper cleanup is necessary. But the cleaning time depends on the sequence of the production. Why is that so? Because basically, if you have, let's say, a batch of red items, okay, when you produce these red items, and then after that, this is, let's say, a batch of red items, then after that we switch to white, okay. So if there are pigments of red color on the machine, then this white becomes reddish, okay, it will not be pure white. But if you first produce white and then shift to red, if on the machine there are some pigments of white color, still this red will be red. Okay, small quantities of white color will not change the red color. But for example, after a black color, if you switch to white color, then even a single drop of black color will make this white color to something like gray. Okay, so it means that if you want to switch from black to white, then you need to clean up more. If you want to switch from white to red or white to black, then a smaller, shorter cleanup is okay. If you want to switch from red to white, again you need to make a proper cleanup. Okay, so the cleanup time depends on from which color you are shifting to which other color. And the question is this: okay, we want to produce these batches of white, yellow, red, and black paints, and we know the individual switch times between each pair of these colors. And the question is, find the sequence of these batches, daily production, that will minimize the total cleanup time. Okay, total cleanup time. And what happens? So if you start from white, then you may go to red, then to black, then to yellow, and at the end you will return back to white again. Okay, so because the next day you will follow the same sequence again. So we want to minimize the total cleanup time in between these switches of batches. The necessary cleanup time is given in this table. Okay, so look, from if you want to switch from white to yellow, you need to make a cleanup of 10 minutes. From white to black, you need to clean up 17 minutes. But for example, from black to white, you need a cleanup of 50 minutes because, as we said, even a single drop of black color may change the color of the white. So therefore, you need to make a proper cleanup. And you see in this table, we can see all the switch times. And the question, is this a TSP problem? And of course, yes, it's a TSP problem because we need to start from one of these colors. Then we need to make the production. We need to find the colors at each step. And at the end, we will return back to the starting color. Although we are talking about changing of the batches, changing of the colors, we are not talking about visiting cities, but the idea is the same, and this is a TSP problem. In this example, there are only 4 different colors, or in terms of TSP, there are only 4 nodes, 4 cities to visit, and in our previous lecture we said that the total number of different tours that we can have is n-1 factorial. Okay, n-1 factorial, and for this case it is 4 minus 1 factorial, which is 6. Okay, so we can try all possible combinations. We may assume that we are all starting with the white color, and I explained this previously. If you don't want to start with the white color, you can assume that the starting color is Y, and if you generate all sequences, in fact those sequences will be the same with this one, because since this is a tour, wherever you start the tour, it will still have the same total distance. Okay, so for each combination of these cities, we can calculate the total cleanup time, basically using the given matrix. And in this example, we see that the best solution is this one, in which case we start from the white color, then shift to yellow, then to red, to black, and back to white. And in total, we make a cleanup of 98 minutes. Okay, so by making total enumeration, trying all possible combinations, we are able to find the best solution for this example. But what happens if you have 11 different colors? Then, if you want to solve it using this complete enumeration, you need to evaluate 11 minus 1 factorial, which is more than 3,500,000 different combinations, and trying all of these and finding the best is impossible or very difficult. So it means that we need a more intelligent way. What we can do is we can formulate this problem, develop the mathematical programming formulation, and use branch and bound or cutting plane algorithms to obtain the best solution. So let's formulate this problem. In the previous lecture, we already developed the general formulation for TSP. Basically, in that version, Dij represents the distance from city I to city J. But here, we will say that this is the cleanup time, okay, from color I to J, and Xij will be a binary decision variable again if we switch from color I to color J. Okay, so the definition of the decision variable will be changed according to the problem, but the formulation will be exactly the same. Minimize this total sum subject to, okay, we have these assignment constraints. The first one saying that from each color I, we will shift to one other color. Okay, if you consider white, from white you can either shift to yellow or to black or to red. You cannot shift to two of them. Okay, so if it is red, you can only switch to red. The second one says that to each color, let's say white, you need to come from one of the colors, either from yellow or black or red. You cannot visit or you cannot switch to white color from two others. Okay, so basically, for example, if you say this will be yellow. And then, of course, these two are the assignment constraints, and last time we said that this part of the problem is identical to the assignment problem. But if you ignore the other important constraint, then you may end up with subtours, and the other important constraint is called the subtour elimination constraints. And the important thing about these subtour elimination constraints is this constraint is written for all possible subsets of the colors in this case, or the cities in the classical definition. And it means that you have an exponential number of constraints, exponential number of constraints. When I say exponential number, here last time we said that you will have 2 to the power n minus 1 constraints. Okay, since this n, which is the number of cities, it appears as an exponent to 2, we call it this as an exponential number of constraints, and it means that writing all such constraints is very difficult. I mean, not solving the problem, even writing the constraints is difficult. Okay, in Cplex, how will you write these many constraints? Okay, it's very difficult. You may write some codes to generate all possible constraints, but even for Cplex, starting to solve the problem will take a lot of time. Therefore, we need another intelligent way. So for this problem, let's write the formulation in open form so that you can understand it better. As I said, in this version of the problem, we will define our xij to be a binary variable if we shift from paint I to paint j. Okay. And remember our matrix, so this shows us the cleanup time. So from white color to white color, the switch time, okay, so you cannot go from white to white. Therefore, we place an infinite over here as a value. And you cannot use infinity in Cplex. You need to write a numerical value. Therefore, we represent it by big M. Okay, so therefore, this big M represents that big number. Then our objective function, if we write using this decision variable, our objective function will be this. M times switching from white to white. 10 times white to yellow. So this 10 is given in the matrix. Okay. 17 times white to black, 15 times white to red, and etc. And in fact, if you don't want to write this as WB and etc., so you can say that, let me write this as white, and then we have yellow, red, and black. And you can say that white is represented by number 1, yellow is 2, red is 3, and black is 4. And here what you write is you basically say M times x11, white to white, plus 10 times x12, white to yellow, plus 17 x white to black, so it is, let me say, 1 to 4. Okay, so you can use these numerical values, and you know that this 1 corresponds to white, 4 corresponds to black, and etc. Okay, so if you write all those values, this will be our objective function. What about the constraints? Again, let's write the constraints in open form, and it will be more clear to understand. So for each color, we need to write 2 assignment related constraints. The first one is from each color, we need to switch to another color. So for example, if we consider white color, okay, from white, we need to go either to yellow or to black or to red. Of course, you can include from white to white as well, but since the cost of this one is infinite or big M, it will not select. So if you like, you can just ignore this one, don't write, or if you like, you can write it, but since in the objective function this cost is very large, it will not select. So in this version, we are writing all alternatives. So for white color, we can switch from white to white, or white to yellow, or white to black, or white to red. And we need to select one of them. You cannot go to 2 of them. You cannot go none of them. You need to go exactly one of them. Therefore, this is equal to 1. Basically, this is assignment. So this second one is written for yellow color. The third one is for black color. And the fourth one is written for the red color. And basically, this says that from one color, you will switch to another color. In the second set of constraints, again, we are saying that for each color, let's say white, we need to switch to this color from one other color. It can be either white or yellow or black or red. So the first one of these constraints is written for white color. So it says from white to white, yellow to white, black to white, and red to white must be exactly equal to 1. Okay? It means that from one of these colors you will switch to white, and again from white to white the cost is infinity. It means that it will not select in the optimal solution to go from white to white, because if you go from white to white, then it means a subtour of a single city, and we don't like such subtours. Okay, then the second one is written for the yellow color, white to yellow, yellow to yellow, black to yellow, and red to yellow. And similarly, we write for black and for red. As I said, for each color, we have two constraints. Okay, this is for white color, these two for yellow color, these two for black color, and these two for red color. And this part is only the assignment part. Then we need to have a subtour elimination constraint to avoid all those subtours. Now I want to write some of the subtour elimination constraints in open form, so you can understand better. Last time, remember, we have written the subtour elimination constraints in compact form like this. Summation I in a subset S, J is not in this subset S, Xij should be greater than or equal to 1, and we said that we should write this for all subsets of the total cities or the total colors for which the cardinality of this subset is greater than or equal to 2. Okay, we have written the subtour elimination constraints in this way. So how can I write? Since this is, we need to write this for all subsets with cardinality greater than or equal to 2, I can consider this subset. Remember, my set of colors is 1, 2, 3, and 4. Okay, and what are the subsets of this? Empty set is a subset, right? So the 1, 2, 3, and 4 are also subsets. But since, because of this, I don't need to write the subtour elimination constraints for these subsets, because we already put a big M value for these switches and we avoid them. And then we have subsets with two elements, which are 1 and 2, okay, 1 and 3, 1 and 4, 2 and 3, 2 and 4. So I didn't write 2 and 1 because 1 and 2 and 2 and 1 are the same sets. Okay, I am continuing from here. 3 and 4. So okay, so these are the subsets with two elements. Then we may have subsets with 3 elements. What are they? So 1, 2, and 3, 1, 2, and 4. Okay, then we may have 2, 3, and 4. And 1, 3, 4. Okay, these are elements with 3. These are subsets with 3 elements. And finally, we have the subset with 4 elements, which is 1, 2, 3, and 4. Okay, so in fact, this 1, 2, 3, and 4 is the tour that we want. There's no subtour here, so we don't need to write a subtour elimination constraint here. Okay, let's consider these 3 element subtours. 1, 2, 3. We want to write a elimination constraint for this one. But it means that if we have a subtour between 1, 2, and 3, then the remaining one is the 4, which means that we will have such a subtour. And since we eliminated this subtour by writing a big M in the distance matrix, it's clear that we will not have such a subtour again. So it means that we don't need to write a subtour elimination constraint for 3 elements. Okay, so we just eliminate it from the single element. So therefore we don't need these subtours again. So the only remaining ones are the subsets with 2 elements. And now let's consider this. So if we have a subtour between 1 and 2, so this is 1 and this is 2, and we have a subtour between 1 and 2. And if we have a subtour between 1 and 2, it means that we have a subtour between 3 and 4. Okay? And if we eliminate this subtour, we automatically eliminate this one. Okay, so if we write the subtour elimination constraint this 1 and 2, we don't need to write the subtour elimination constraint for 3 and 4. So we need only one of these pairs. Again, for 1 and 3 and 2 and 4, these are pairs. Okay, let me sketch like this. And 1 and 4 and 2 and 3 are pairs. Okay, so for these pairs, we only need to write one of them, and we can eliminate the other one automatically. It means that for this example, we are going to write only 3 subtour elimination constraints. What are they? So let's consider this case. 1 and 2, there is a subtour between, and this is our set S. Okay, and we have the other cities, which are 3 and 4. And according to my constraint over here, I need to say that, okay, either there will be an exit from 1 to 3 or 1 to 4. So this 1 is inside S, 3 is not inside S. 1 is inside, 4 is not inside. Plus 2, 3 plus 2, 4. And this number should be greater than or equal to 1. It is not equal to 1. Look, it is greater than or equal to 1 because it can be 2, it can be 3. So from this set S to the outside and the other cities, we may have multiple exits, not from the same city, from different cities. We may go from 1 to 3, and we may go from 2 to 4, and this number is not 1, you see? Okay, so this is the first constraint. Now let's consider the other one, which is 1 and 3. This is our set S, and the other cities are 2 and 4. Okay, so it means that we need to say from 1 to 2, or 1 to 3, or 3 to 2, or 3 to 4, we need to have at least one exit. So this is the second subtour elimination constraint. And what about the last one? It is in set S we have 1 and 4, and outside we have 2 and 3. And the constraint should be x12 plus x13 plus x42 plus x43 should be greater than or equal to 1. Okay, so this is the third subtour elimination constraint. In this example, we only needed 3 subtour elimination constraints. Together with the earlier assignment constraints, we can enter this into Cplex or any optimization software and get the optimal solution without any subtours. But as the number of cities increases, the number of subtour elimination constraints that you need to enter also increases. Therefore, we need another method to solve these TSP problems. Now we are going to learn a branch and bound algorithm to solve this TSP. In fact, we learned the branch and bound algorithm, but here we will have another idea. We will use another idea which is very clever, but still it's a branch and bound algorithm. Remember, in the classical branch and bound algorithm that we learned, what we do in this TSP problem, we have these xij variables which are binary variables. And first, what do? We convert these xij we relax them and we convert them to be variables between 0 and 1. Okay, for all I and j, and we solve this relaxed problem in the root node and then select one of the variables to set it equal to 0 or equal to 1 and branch and go on. But here, the thing is, when the number of cities is too much, the number of subtour elimination constraints is too much. It means that if you relax the problem in this way, still it is not easy to write all subtour elimination constraints because there is a huge number of constraints. What is the idea of relaxation? The idea is to obtain a simple problem to solve. After relaxing, we need to have a simple problem. And the thing is, I am saying it again and again, the formulation of the TSP is similar to the assignment problem unless these subtour elimination constraints. That is the more complicating constraints. Okay, when we don't include the subtour elimination constraints, the resulting formulation is assignment problem, and assignment problem is easy to solve. Okay, and what is a relaxation? Again, let's go back to our earlier lectures. Let's remember those. A relaxation is eliminating a constraint or making a constraint easier to solve. Make it easier. Okay, in the TSP formulation, if we eliminate the subtour elimination constraints, if we delete them, if we ignore them, then the remaining formulation is the assignment problem, and that assignment problem is a relaxation of the TSP. Okay, so we can obtain a relaxation of TSP by just ignoring the subtour elimination constraints. So the idea of the branch and bound algorithm for the TSP is relaxing the problem not by relaxing the decision variables, but by eliminating or deleting the subtour elimination constraints. Okay, so let's first see the steps of this algorithm, and then we are going to solve our example using this algorithm. What do? First, we relax the subtour elimination constraints. In fact, it is not written here, but I can write as the first step. Relax, when I mean relax, just ignore or delete. Relax the subtour elimination constraints. Okay, this is the first thing. Elimination constraints. And then solve the resulting assignment problem. And when you solve this problem, we start with the optimum solution of this assignment problem. If in the optimal solution there is no subtour, there is only a single tour which contains all of the cities, then we stop. It means that we found the optimal solution for the TSP. This is the same thing when you relax a decision variable in regular mathematical programming based branch and bound. When you solve the root node, if all decision variables are integers, then you stop. And this is the same idea. When you solve the relaxed problem and get the solution or observe the solution that already satisfies the relaxed constraints, then you stop. Otherwise, if there are some subtours, what do? We include constraints to avoid subtours. We are not just including xij is 0 or xij is equal to 1. We need to add constraints to avoid these subtours and then continue solving the problem. Okay. Okay, so let's assume that we solved our relaxed problem here in the root node and assume that we have a subtour. We have a subtour, let's say between city 1 and let me use just a simple example. Between city 1 and 3, let's assume we have a subtour, and it means that in our example, since we have only 4 nodes, 2 and 4, there is another subtour. Now I need to branch since we have subtours, and now I need to include the necessary constraints to eliminate these subtours. But what are those constraints? So you need to be careful. You need to be very careful here. Pay attention. So in order to eliminate this subtour, what do we have? This is x1, 3, right? We are going from 1 to 3. And this is x3, 1. It means that we are returning back from 3 to 1. So how can I eliminate these? In two ways. Either I will set x1, 3 equal to 0, so that initially it was 1, so that this arc is broken and we are not going from 1 to 3. Or I would say x3, 1 is equal to 0, so that we are not going from 3 to 1. Okay? So be careful. In classical branch and bound, if we were using that, after this relaxed problem, we were saying that either x13 is equal to 0 or x13 is equal to 1. But now you see we are using a different variable, x13 here and x31 here, and we are setting both of them to be equal to 0, not one of them to 0 and the other one to 1. Okay, so this is a different idea than the classical branch and bound. Pay attention to here. And the basic reason that we do in here is we are adding the necessary constraints to eliminate the subtour. And that necessary constraint is to set either the switching from 1 to 3 to 0 or 3 to 1 to 0. And now you may say that, okay, but there's another subtour here. Why did you select it 1, 3, 3, 1? We could have used it, okay? But you don't need to use both of them at the same time, because if you just avoid the subtour between 1 and 3, the other one will automatically be eliminated. So therefore, you don't need to include all of them. But you could have done this. x24 equal to 0 to eliminate this switch, or x42 equal to 0 to eliminate returning back. Okay, so again we branched. So either you apply this one or you apply this one, you will find the same, or you will find the same objective function value. You will be able to find it. There is no rule for selecting these, but usually what do we do? If, for example, instead of 2 cities, if we had 3 cities like this, instead of 4 cities, if we had 5 cities, what would we have? We will have, okay, from 1 to, let's say, 3, there is a subtour, and the other subtour will contain 2 to 4 to 5 and to 2. Okay, with 5 cities, we may have, if one of the subtours is with 2 cities, the other one will be with 3 cities. Then, in order to branch, or in order to write the branch and bound algorithm, we can use either this version or this version. So the branching, if we make branching with respect to the first subtour here, we would say, okay, this is the root node. Then in order to eliminate this first subtour, you see the elimination can be done either by eliminating x13 to be equal to 1, or eliminating x3 or avoiding x31 to be equal to 1. We can avoid one of them. So we can say that x13 is equal to 0 on one side, and on the other side we can say x31 is equal to 0. So this is how we write the branching with respect to this one. Now the problem is, If we decide to write the branching with respect to the other one, with respect to this, how shall we do it? Again, be careful. This is a very clever idea for TSP, but it is different than our regular or classical mathematical programming based branch and bound. Now, the things that we did over there changed a little bit. Okay, be careful with that one. So what is the idea? We need to eliminate this subtour. Okay, and eliminating this subtour can be done in how many different ways? Until now, we always branched into two. But be careful, we need to consider all alternatives here. So it means that in order to eliminate this one, look, what do we have? We have x24 equal to 1, so it means that we are switching from 2 to 4. We have x42 equal to 1, we are switching from 4 to 5. And we have x52 equal to 1, which means that we are switching from 5 to 2. So it means that we need to eliminate at least one of these so that there is no subtour. Then it means that this branch and bound tree, either we will set x24 equal to 0 so that we eliminate this switch over here and we will not have this subtour, or we can eliminate this one for 5, or we can eliminate this one 5 2. Eliminating any one of these will eliminate the subtour over here. If you do not write all of them, if you ignore one of them, if you just branch into 2, then it's a mistake. You will not be able to get, you may not be able to get the optimal solution in this way. Okay, so be very careful with this idea of branch and bound. The idea is we first relax the subtour elimination constraints. Then when we solve the relaxed problem, if there is a subtour, we write all the necessary constraints to eliminate that subtour. And if there is a subtour, if you want to branch on a subtour with 3 cities, then you need to branch it into 3, not 2. If there is a subtour, if you are going to write a branching with respect to, let's say, 4 cities, a subtour with 4 cities, then you need to branch it into 4. So the branch and bound algorithm for TSP is not only does not only branch into 2. It may branch into 3, into 4, into more, okay, depending on the size of the subtour. Be very careful. And now the question is, if you have a TSP with 5 cities, like the example we have here, and we have 2 subtours. In one side, the subtour has 2 cities, and on the other side, the subtour has 3 cities. And you want to have this subtour, you want to write this subtour elimination constraints. Will you prefer this alternative with 2 cities or this alternative with 3 cities? Both of them will avoid or will prevent the subtours. Which one will you prefer? If you select this alternative, you will branch into 2. If you select this alternative, you will branch into 3. So therefore, since it is easier to branch into 2 and it's less time demanding, we select this alternative. Okay, so whenever you have more than one subtours, then use the branch and bound algorithm, use branching to prevent subtours with smaller number of cities. Okay, so this is how we make these branching. We are setting both variables equal to 0 in TSP case. Now, what happens if we solve a problem, and in that problem, so let me write it here. Let's assume that we started from this one and then we branched and then we solve this node 1, and there is no subtour here, no subtour. What's our decision? So it means that we found a feasible solution, which means that we need to fathom by solving or by optimal solution. And do we stop the branch and bound algorithm? Does it mean that we found the optimal solution? No, because we haven't investigated this yet. The idea is the same with the regular branch and bound algorithm. We fathom this node by solving, and we say that, okay, we found a feasible tour. Is this a better solution than my earlier incumbent solution? If so, we update the incumbent. If not, we use the previous incumbent. So since this is a minimization problem, incumbent solution provides us an upper bound. Then we continue with the other open nodes. But if there is no subtour, if there is a subtour in this node, then you cannot fathom. You need to check. You need to check if you can fathom because of bounding, and if you cannot fathom, then you need to branch this furthermore, and according to whether you are following depth first search or breadth first search, you will select one of the nodes and continue. So like in the regular branch and bound algorithm, classical branch and bound algorithm, we continue this branching procedure until there are no unexplored nodes. Okay, when we fathom all the nodes. So when you solve, there can be two cases, okay, to fathom. If that solution, that feasible solution, has a worse, let's say, solution than our previous incumbent solution, then it means that we can fathom that node here. Also, if there is a subtour in the branch, in this branch, so let's assume that we have a branch and bound tree, we solve these and etc. Now we solve this one, and there is still a subtour here, okay, with a value of 100, let's say, but we already have an incumbent solution until this node, which has a value of 90. So for a minimization problem, this 90, it's a feasible tour. This 90 is less than 100. And it means that if you continue branching on this node, you will not obtain a solution with a total distance less than 100. So it means that you can fathom because of bounding. Okay, so you can fathom due to one of these two reasons. And when you complete all nodes, when there are no unexplored nodes, we stop. And when you stop, the incumbent solution in your hand is the optimum solution for this TSP. We are going to solve this example problem in our next video lecture using this branch and bound procedure. But if you like, you can try to solve it by yourself. Remember, we are relaxing the subtour elimination constraints, and the remaining problem is assignment problem. And how do we find the solution of an assignment problem? We already learned the algorithm, which is called Hungarian algorithm, right? You can use this algorithm to find the solution to this relaxed problem. So it means that you need to know this algorithm. Okay, now assume that we have this branch, we solved the problem, and we obtained, let's say, a subtour between 1 and 4. For this example, we have 5 cities. And then we have another subtour between 2, 3, and 5. Between 2, 3, and 5. Okay. Now we are going to branch, and we said that when you have two subtours or more than one subtour, select the one with less number of cities, which is this one. Then in order to avoid this, you see we have x14 is equal to 1 over here, and from here x41 is equal to 1. And if we have both of these two at the same time in the solution, it indicates a subtour. Then I need to avoid one of these, at least one of them. So we say that x14 equal to 0 or x41 equal to 0. We need to include this. And when you do this, in your problem, when you just write this as a constraint into your problem, now it becomes something different than the assignment problem. Because in assignment problem, there is no such a constraint. There shouldn't be such a constraint. In order to be able to use the Hungarian algorithm again, you shouldn't have this. But still, be careful. x14 equal to 0. What we want to satisfy? We don't want the solution or the tour to go from 1 to 4. We want to eliminate that switch. And how can we do it? Look, this is city number 1. This is 1, 2, 3, 4, and 5. And currently the subtour passes through from 1 to 4, and we want to eliminate this. And without writing this constraint, we want to eliminate this. How can we do it? Basically, we just update this cost matrix over here, or the distance matrix, and instead of having 6 over there, we write a big number, big M. And when you write it, you eliminate from 1 to 4. If you want to go to the other side, and if you want to eliminate this one, what do we do? You keep this old one the same, it's still 6, but from this is city 2, 3, 4, and 5. Okay, this is the time from switching from 4 to 1. And what do? We change this from 7 to big M, so that we include this constraint. Okay, let's say after that we decided to branch this one as well, and now we need to write x25 equal to 0. I need to eliminate that switch. What should I do? Since this branch over here includes this one and this one at the same time, so I need to keep this M over here, and also I need to change this switching from 2 to 5 to big M at the same time. Okay, but if I need to write x52 equal to 0 over here, then I need to shift this back and say that, okay, x52, this one, I need to make it equal to M. Okay, in fact, inserting a constraint into this branch and bound in the TSP is just converting an element in the distance matrix to a big M value. Okay, so I gave you this idea. In the next lecture, we are going to solve this example using the branch and bound method. But before that, by yourself, please try to solve it. You can use this assignment algorithm, the Hungarian algorithm, to solve these problems. And whenever you have a subtour, then you need to branch, and then you need to adjust the cost matrix or the distance matrix, and then apply the assignment procedure again to solve it, and you need to obtain the optimal solution. You can find the solution in the next lecture.